A spacecraft the size of a small car is 15 billion miles from Earth, moving at 38,000 miles per hour on computers less powerful than a digital watch. In 2023, it started sending back something nobody had ever seen. Not silence, not a clean signal, but broken, looping gibberish from interstellar space. NASA could not send a repair crew, could not replace the hardware, and that crisis opened something bigger, because Voyager 1 has been wrong about everything we thought we knew for 50 years. Wrong about the boundary of the solar system, wrong about what lies beyond it, wrong in ways that are still unfolding right now. Subscribe if you want to follow this investigation. We are going all the way in. In November 2023, something went wrong with the most distant machine humanity has ever built. Engineers at the Jet Propulsion Laboratory in Pasadena, California, sat with a problem they could not immediately solve. Voyager 1 was still transmitting. The radio signal was still arriving after a journey of over 15 billion miles through interstellar space. But the data inside that signal had stopped making sense. The flight data system, the onboard computer responsible for packaging science readings and health data into a format engineers could understand, was producing gibberish, garbled binary loops, repeating patterns with no coherent information, a machine cycling through its own confusion. It was talking to itself in a language no one on Earth could decode. The delay between Earth and Voyager 1 at that point was 22.5 hours, one way. Send a command, wait 22.5 hours. Receive a response, wait another 22.5 hours. Any troubleshooting attempt required 45 hours of patience before you knew whether your idea had done anything at all. And because the spacecraft was so far beyond the reach of any repair mission, every decision carried a weight that no other engineering problem in history had carried quite so completely. There was no backup option. There was no second chance to try a different approach in person. There was only the signal, the weight, and the hope that whoever had built this machine 5 decades ago had left enough clues inside its aging systems to guide a repair from across the solar system. Project manager Suzanne Dodd said publicly that this ranked among the most serious crises the Voyager mission had ever faced. That statement carried real weight for anyone who understood what Voyager 1 actually represents. This is not a spacecraft that can be replaced with a newer model. This is not a sensor platform that has a sibling doing similar work somewhere else in the outer solar system. Voyager 1 is the only human-made instrument ever placed in interstellar space. Every reading it takes is the first of its kind. Every measurement of plasma density, magnetic field strength, or cosmic ray flux in the space between stars is data that no other mission has come close to collecting. There is literally nothing else out there doing this work. No fallback, no plan B. To understand why that matters, you have to understand what it took to get it there, what it found along the way, and how many times what it found forced scientists to acknowledge that their models of the universe were wrong, not slightly off, not in need of minor adjustment, fundamentally wrong. The story of Voyager 1 is not a story of smooth scientific progress toward confirmed expectations. It is a story of surprise after surprise, of instruments designed to measure one thing, revealing something nobody had predicted, of boundaries assumed to lie at one distance, turning up somewhere else entirely. Of science done in real time on a problem that had never been solved before, with hardware that was already ancient by the standards of any decade after the one in which it was built. But in November 2023, none of that history could fix the problem in front of the team at the Jet Propulsion Laboratory. The spacecraft was alive, it was transmitting, and it was saying something none of them could understand. Nobody knew yet whether this was the beginning of the end of the only mission that had ever crossed into the space between stars. The window that made Voyager 1 possible opened exactly once in any human lifetime, and a young aerospace engineer named Gary Flandreau was the person who noticed it. It was 1965, and Flandreau was doing trajectory analysis at the Jet Propulsion Laboratory as a summer student. His assignment was to catalogue possible flight paths to the outer planets, and what he found was something nobody had quantitatively mapped before. Jupiter, Saturn, Uranus, and Neptune would achieve a geometric alignment in the late 1970s that would allow a single spacecraft to use each planet's gravity as a sling and visit all four in sequence. This configuration repeats only once every 176 years. The next occurrence, after the 1970s window, would fall in the 2150s. Miss it, and no one alive in 1965 would ever see another one. NASA approved what would become the Voyager program and set about designing trajectories with urgency. More than 10,000 possible flight paths were analyzed. Engineers had to weigh science return against fuel budget, against planetary geometry, against the limitations of every system on a spacecraft that had not yet been built. Voyager 2 launched first on August 20th, 1977, aboard a Titan III IE Centaur rocket. Voyager 1 followed 16 days later, on September 5th, 1977, on a faster trajectory. Despite launching second, Voyager 1 overtook its sibling on December 15th, 1977, while both spacecraft were crossing the asteroid belt. Voyager 1 has been the farther one ever since. The machines themselves were extraordinary things to send into the unknown. Each was designed to operate for 5 years. That was the official mission life. 5 years. The radioisotope thermoelectric generators, which convert the heat of decaying plutonium into electricity, were producing roughly 470 watts at launch. The onboard computers had less processing power than a cheap pocket calculator sold in any drugstore at the time. The camera systems, the magnetometers, the plasma instruments, and cosmic ray detectors, all of it had to survive the radiation belts of Jupiter and the thermal extremes of deep space, built to tolerances that no one had ever tested beyond simulations and educated guesses. What they carried was equally deliberate. Each Voyager holds a golden record, a 12-inch gold-plated copper disc encoded with sounds and images selected to represent life on Earth. Music, greetings in 55 languages, the sounds of wind and surf and animals and engines. Anne Druyan served as creative director for the record, and during the process of its creation, she fell in love with Carl Sagan. The two married. Druyan's brainwaves were recorded directly onto the record as she meditated on a series of thoughts about life on this planet. The specific mental state captured there was, by her own account, one in which she was thinking about falling in love. That is now encoded in a physical object traveling through interstellar space. Whether anything will ever hear it is unknown and will likely remain unknown for a very long time. But in the 1970s, the question was not what came after the record. The question was whether any of the science instruments would survive long enough to return useful data. The 5-year design life was already being treated as an optimistic estimate by some inside the program. Nobody seriously expected what would actually happen. Nobody had designed for 40 years, let alone 50. What the spacecraft found at Jupiter would already prove that the universe near this star was stranger than anyone had mapped. Nobody was looking for volcanoes on Io. That was not among the scientific hypotheses being tested when Voyager 1 made its closest approach to Jupiter in March 1979. Io was assumed to be geologically dead, a battered moon whose craters and surface features had been set in place billions of years ago and had not changed since. This was a reasonable assumption. The moon is geologically dead. Mars is largely quiet. The outer solar system was not thought to be a place of active geology. There was no strong theoretical reason to expect otherwise. On March 8, 1979, a navigation engineer named Linda Morabito was processing images taken by Voyager 1's cameras. Her task was precise. She was looking for background stars in the image frames to use as reference points for calculating the spacecraft's exact position. It was methodical work, the kind of work that never makes headlines, calibration and measurement in service of keeping the spacecraft on course. And then she saw something on the edge of one of the Io images, a large, crescent-shaped structure rising above the limb of the moon. She thought at first she was looking at another moon, perhaps a small one positioned just behind Io in the frame. She was not looking at another moon, she was looking at a volcanic plume. It was erupting from the surface of Io and rising 300 miles into space. That plume was, at the moment Morabito noticed it, the first active volcano ever observed on any world other than Earth. It was confirmed to be volcanic in origin within hours of the discovery. Additional analysis of the Io images quickly revealed at least 8 distinct eruption sites. Io was not dead. It was, in fact, the most volcanically active body in the entire solar system, orders of magnitude more active than Earth. The question was immediate. Why? Io is far from the star at the center of our solar system. Its surface temperature averages around -230 degrees Fahrenheit on the night side. There is no obvious internal heat source analogous to the radioactive decay that keeps Earth's core warm. The answer, once worked out, came from a process that had been dramatically underestimated in the models. Tidal heating. Io is locked in orbital resonance with Europa and Ganymede, 2 of Jupiter's other large moons. The gravitational pulls of these bodies, combined with Jupiter's enormous gravity, flex and squeeze Io's interior continuously. The process generates enough heat to keep vast reservoirs of magma molten and erupting. The calculations had been done, the mechanism had been theorized, but the magnitude of the effect was wrong by enough to make the difference between a dead moon and the most active volcanic body in the known solar system. Scientists had built models of Io based on incomplete data and underestimated assumptions. Those models said quiet. The spacecraft said otherwise. This would become a recurring pattern throughout the Voyager mission, a theme that repeats at every boundary, every moon, every region of space where human instruments were making first contact with reality. The theory was not useless. It pointed in a broadly correct direction, but it missed the actual magnitude by enough to be functionally wrong. A navigation engineer, checking star positions for routine calibration, had just overturned decades of planetary science, and Voyager 1 still had Saturn waiting ahead. When Voyager 1 arrived at Saturn in November 1980, the scientists watching the data come in were not prepared for what the rings would turn out to be. The pre-mission models had predicted a relatively simple structure, a few broad bands separated by distinct gaps. Clean, organized, the product of gravitational resonances with Saturn's moons sorting material into predictable zones. The reality was something else entirely. Voyager 1's cameras and instruments revealed not a few broad bands but thousands of distinct ringlets, each following its own orbit, each with its own density and composition profile. Some ringlets were slightly elliptical rather than perfectly circular. Some showed evidence of waves propagating through the ring plane. The F-ring, a narrow outer ring that the models had predicted to be a simple strand, turned out to be braided. Multiple strands twisting around each other in a structure that had no precedent in classical orbital mechanics. The photographs were so strange that several researchers initially suspected instrument error. The B ring, the broadest and brightest of Saturn's ring system, contained features called spokes, dark radial markings that appeared and disappeared. They rotated with Saturn's magnetic field, rather than following the orbital mechanics that governed everything else in the rings. Material orbiting at different distances from Saturn should move at different speeds, because orbital velocity decreases with distance. The spokes violated that rule. They rotated as if locked to the planet's magnetic field, not to gravity. No one had predicted this. No mechanism was immediately available to explain it. The consensus explanation that eventually emerged involved electrostatically charged fine particles being lifted and suspended by magnetic forces, but the details were contested for years. 2 small moons, later named Prometheus and Pandora, were found orbiting just inside and just outside the F-ring. These shepherd moons, as they came to be called, were exerting gravitational forces on the ring material that helped maintain its sharp edges and its braided structure. The discovery of shepherd moons was not entirely surprising in concept, but the specific mechanics of how Prometheus and Pandora interacted with the F-ring proved to be chaotic and variable, not the steady, predictable shepherding the models had assumed. The overall picture that emerged from the Saturn encounter was of a system orders of magnitude more complex than anything the pre-mission models had sketched. Every prediction about ring structure had been made on the assumption that gravity alone, plus a handful of major resonances, governed the system. What Voyager 1 found was that magnetic fields, electrostatic charges, the gravitational chaos of multiple small moons, and other mechanisms not yet fully understood were all contributing to a structure that continued to surprise researchers for decades after the flyby. Scientists who had spent years building models of what Saturn's rings should look like had to begin again from a much more humble position. The spacecraft made its closest approach to Saturn on November 12, 1980. After that, its trajectory bent upward, out of the plane in which all the planets orbit, and pointed toward deep space. Saturn was the last planet Voyager 1 would ever see up close. The reason for that had been decided years earlier, before launch, and it had everything to do with a moon and a decision from which there would be no return. The decision to prioritize Titan was made before Voyager 1 ever left Earth, and it was not made lightly. Titan, Saturn's largest moon, had been observed from Earth to possess an atmosphere. That made it the only moon in the solar system known at the time to have one. Some theorists believed that Titan's atmosphere might be thick with nitrogen and complex organic compounds, that it might resemble, in some chemical sense, a deep frozen version of the chemistry that preceded life on Earth. These were extraordinary possibilities. The scientific community wanted a close look, and Voyager 1 was the machine positioned to provide one. Getting close to Titan required routing the spacecraft through a specific corridor near Saturn, and that corridor sat above the plane in which the planets orbit. The gravity assist from that geometry would bend Voyager 1's path permanently upward and outward, away from the ecliptic, the flat disk where every future planetary encounter would otherwise have been possible. The implication was clear and accepted. After the Titan flyby, Voyager 1 would never pass close to another planet. There were no more worlds in its corrected path. The mission planners knew this. They chose Titan anyway. The scientific value was judged to be worth the permanent sacrifice of all future planetary encounters. What that meant in practice was that Voyager 1 would become, after November 1980, a spacecraft aimed at interstellar space, with no intermediate destinations and no timeline for encountering anything. On November 12, 1980, Voyager 1 made its closest approach to Titan at roughly 3,900 miles from the moon's cloud tops. The cameras were ready. The science teams were ready. The models had suggested there might be a thin atmospheric haze, partially transparent, beneath which the surface would be visible. The cameras saw nothing useful. Titan's atmosphere was not a thin veil. It was an opaque wall of orange-brown smog wrapping the entire moon from pole to pole, completely blocking any view of whatever lay beneath it. The surface would remain unknown for another 25 years, until the Huygens probe finally descended through that haze in 2005 and returned the first images from Titan's ground. The data Voyager 1 did gather about Titan's atmosphere was scientifically important. It confirmed nitrogen as the dominant gas, identified complex organic molecules, and measured surface pressure at roughly 1.5 times Earth's. Those findings were real and valuable. But the orange blankness in the camera frames was a peculiar kind of defeat, a reminder that a decision made years earlier had cost the mission its future planetary encounters, and the thing it traded them for had refused to show itself. After Titan, the trajectory carried Voyager 1 upward and outward with nothing ahead but distance. No more planets. no more gravity assists, no more science targets on any map that existed at the time. The spacecraft had left the known itinerary entirely. It was still transmitting, it was still operational, but what it was heading toward had no name yet, no confirmed distance, no agreed-upon boundary. Nobody knew exactly where the solar system ended. Nobody had yet established, with any certainty, what the transition out of the solar system would look or feel like to an instrument designed in the 1970s. Voyager 1 was going to find out if it lasted long enough. That was, by late 1980, very much an open question. By 1990, Voyager 1 was approximately 3.7 billion miles from Earth. It had traveled roughly 40 astronomical units outward from the star at the center of the solar system, where 1 astronomical unit equals the average distance between Earth and that star. The spacecraft's cameras had been shut down for nearly a decade. There was no scientific reason to keep them powered, because there was nothing to photograph. Deep space was empty of anything worth the electricity. Carl Sagan changed that calculation. Sagan had been pushing NASA for years to turn Voyager 1's cameras back on one final time and take a portrait of the solar system from the outside. Not for science in the strict sense. For perspective, NASA had reservations. Pointing cameras back toward the star risked damaging optical instruments designed to look outward. The technical and operational arguments against it were real. Sagan persisted. In February 1990, NASA agreed. On February 14, 1990, Voyager 1 captured 60 images in a mosaic sweep of the inner solar system. The star was bright enough to cause optical artifacts in the frames. Most of the planets were too small to resolve clearly. Earth appeared in one frame as a pale blue dot, a point of light less than a single pixel in diameter, fractionally illuminated against the black. That image became one of the most reproduced photographs in the history of space exploration, not because it showed anything scientifically novel, because of what it showed about scale. Sagan wrote about that image. He described Earth as a mote of dust suspended in a sunbeam. He wrote that every person who ever lived and died had done so on that pale blue point. Every war, every act of cruelty, every act of love, every great civilization that had ever risen had done so on a fraction of a pixel. His words have been quoted so many times since that they risk cliché, but the underlying argument has not lost its force. The argument is about proportion, about the difficulty of taking seriously the tribalism and territorial conflicts of a species that occupies so small a portion of a very large universe. After those 60 images were captured, the cameras were powered down permanently. Voyager 1 still carried them, but they would never be used again. The power budget did not permit it. The scientific agenda did not require it, and there was, honestly, nothing to photograph. The spacecraft had entered a region of the solar system so empty that the cameras would return only blackness for the rest of the mission's life. Anne Druyan, who had helped curate the golden record now traveling with Voyager 1, had her brainwaves recorded while she meditated on what it meant to live on Earth, on what it meant to love. She was, at the time, falling in love with Carl Sagan. That emotional state is encoded on the record. Two people whose names became synonymous with the effort to reach across interstellar space began their life together in the process of building the message Voyager carries. Whether anything will ever receive that message remains unknown, but the spacecraft carrying it was now aimed at the edge of the solar system. It was approaching a boundary that had never been crossed, pointed toward a destination that nobody had yet confirmed even existed. For decades, scientists had predicted that Voyager 1 would encounter a specific boundary as it moved outward through the solar system. This boundary, called the termination shock, is the region where the solar wind, the continuous stream of charged particles flowing outward from our star, slows from supersonic to subsonic speeds as it meets the resistance of the interstellar medium. The models were confident about its existence. They were less confident about its exact location. with most predictions placing it somewhere around 85 astronomical units from the star at the solar system's center. That is roughly 7.5 billion miles out. On December 16, 2004, Voyager 1 crossed the termination shock at 94 astronomical units, not 85, 9 astronomical units further out than the central prediction. That was a miss of roughly 800 million miles. The boundary had been pushed outward by the current state of the solar cycle, and while the discrepancy fell within the acknowledged range of uncertainty, it was noted. But the location discrepancy was not the important surprise. The important surprise was what happened to the cosmic ray measurements. Before the crossing, theorists had made a specific prediction. Anomalous cosmic rays, a particular type of high-energy particle that originates in the outer reaches of the solar system, were expected to peak in intensity right at the termination shock. The shock was supposed to be the acceleration site, the place where particles picked up enough energy to become anomalous cosmic rays in the first place. At the crossing point, those particles should have peaked and then dropped off on the far side. That is what the models said. What Voyager 1 actually measured was different enough to force a revision of the underlying theory. At the crossing, anomalous cosmic ray counts were not at their peak. Helium ions were present at only about 10% of the expected concentration. Oxygen ions were present at roughly 5% of what the models predicted. And instead of declining after the shock, the counts kept rising. Into the heliosheath, the vast region between the termination shock and the heliopause, the particle counts continued to climb. The acceleration was not happening at the nose of the heliosphere. It was happening somewhere else, likely on the flanks or in regions of the boundary that Voyager 1 was not positioned to directly sample. This was not a minor calibration error. This was a fundamental flaw in the model of how cosmic rays get accelerated. The assumption that the termination shock at the nose of the heliosphere was the primary acceleration site, which had been a foundational piece of heliospheric physics for decades, turned out to be wrong. The acceleration mechanism was more distributed, more geometrically dependent, and less well understood than the textbooks had stated. Every paper that had confidently described the termination shock as the dominant source of anomalous cosmic rays now required re-evaluation. Voyager 1 had delivered a result that invalidated a major piece of the theoretical framework built to describe the very region it was crossing. Not everyone accepted the interpretation immediately. Alternative models were proposed. The debate continued for years. But the data was what it was. And beyond the termination shock, deeper into the heliosheath, the spacecraft kept pushing outward. The next boundary was waiting somewhere ahead, and nobody was sure anymore exactly where it would be. After Voyager 1 crossed the termination shock in December 2004, it entered the heliosheath, the region between the termination shock and the outer boundary of the solar system's magnetic bubble. This zone had been modeled extensively. The predictions placed it at roughly 40 to 50 astronomical units thick, with the heliopause, the outer boundary where the star's influence ends and interstellar space begins, somewhere around 135 to 145 astronomical units from the star at the solar system's center. The models were based on the best available understanding of how the solar wind pressure balanced against the pressure of the interstellar medium. They had been built over decades. They were wrong by 30 to 40%. Voyager 1 took about 8 years to cross the heliosheath. When the crossing of the heliopause finally occurred in 2012, the spacecraft's instruments placed it at 122 astronomical units. Not 135, not 145, 122. The heliosheath turned out to be approximately 28 astronomical units thick, rather than the 40 to 50 that had been predicted. The solar system's protective magnetic bubble was significantly smaller than the models had sketched. Every diagram of the heliosphere drawn before 2012 that showed the relative proportions of the termination shock distance, the heliosheath thickness, and the heliopause location was wrong in its basic geometry. The compression was real, and it was significant, and it had no clear identified cause. The two forces being balanced are solar wind pressure, pushing outward, and interstellar medium pressure pushing inward. For the heliosphere to be more compressed than expected, either the solar wind was weaker than the models assumed, or the interstellar medium was denser and more pressurized than the models assumed, or some combination of the two. No specific process was identified in the years immediately following the crossing that fully accounted for the discrepancy. Multiple hypotheses were proposed. None achieved consensus. The compression happened, the models were wrong, and the reason for the magnitude of the error remained an open area of research. What made this significant beyond the raw numbers was what it implied for future missions. Heliospheric boundary science had been used to plan expected travel times and science windows for Voyager 1 and its sister spacecraft. The models that proved to be off by 30 to 40% in the thickness of the helio sheath had informed decisions about instrument operation, power budgeting, and mission planning. Getting those proportions wrong by that margin is not a rounding error. It is a structural misunderstanding of how the solar system sits inside the galaxy. Scientists responded by revising the models. That is how science is supposed to work. The data from Voyager 1 was incorporated, new constraints were applied, and improved models were published. But the underlying problem persisted. Voyager 1 crossed the heliosphere at one specific location. It approached the heliopause from one specific direction. The heliosheath thickness it measured was the thickness at that one point. Whether the rest of the heliosphere was similarly compressed, or whether that particular region was anomalous, nobody could say with certainty. A second data point was coming, but it was still years away. And the data coming from Voyager 1, in the meantime, was about to get much more confusing before it got clearer. In the 2 years before Voyager 1's official crossing of the heliopause in August 2012, the data coming back from the spacecraft became deeply contradictory. The science teams were not in agreement. Different instruments on the same spacecraft were telling different stories, and no single model existed that could accommodate all of them simultaneously. This was not the controlled ambiguity of a measurement with large error bars. These were instruments that were working correctly. They were measuring real phenomena and arriving at conclusions that pointed in opposite directions. The particle science data showed patterns consistent with a spacecraft that had crossed the heliopause. The ratio of solar wind particles to galactic cosmic ray particles was shifting in ways the models associated with a transition into interstellar space. Some members of the Voyager team read these numbers and began arguing that Voyager 1 had already made the crossing. The year was 2010, then 2011. Papers began appearing. The claim was controversial. The magnetic field instrument did not agree. The magnetic field inside the heliosphere, the region dominated by the star's magnetic influence, has a known orientation. The interstellar magnetic field was predicted to have a different orientation. A crossing of the heliopause should produce a measurable rotation in the field direction. That rotation was not appearing. The magnetic field measured by Voyager 1 through 2010 and 2011 remained consistent with a heliospheric field, not an interstellar one. Scientists reading the magnetic data argued the spacecraft had not crossed the heliopause. The two groups were looking at the same spacecraft, the same mission, the same data stream. They were not in agreement. The disagreement went beyond interpretation. The underlying physics was in conflict. If the particle data was right, the magnetic field behavior needed an explanation. If the magnetic field data was right, the particle data needed an explanation. Some researchers proposed that Voyager 1 was passing through an intermediate zone, a region that was neither cleanly inside the heliosphere nor cleanly outside it. This zone had no established name. It had not been predicted by any model. It was being proposed in real time to account for data that existing theory could not otherwise explain. The debate was fierce and public. Papers published during this period reflect genuine scientific disagreement. with researchers on both sides citing the same dataset and reaching incompatible conclusions. This is unusual. Science is often portrayed as a process that converges on consensus through evidence. The Voyager 1 data in 2010 through 2012 shows what happens when the evidence is itself ambiguous, when the boundary being crossed is not clean, when the universe does not conform to the categories built to describe it. One factor that would have resolved the debate quickly was a direct measurement of plasma density, which should jump sharply at the heliopause if the spacecraft actually crossed it. The plasma science instrument on Voyager 1 had failed years earlier. The measurement that would have provided the clearest answer was unavailable. The team was working with what remained. They were passing ambiguous readings from aging instruments, 40 or more astronomical units, past the outer boundary of any world ever visited. Some researchers noted that no model had ever predicted this kind of ambiguity, this situation where the data would be interpretable in fundamentally incompatible ways. The crossing, when it was finally called, would not be clean, and even after it was called, the disagreement would not fully end. On August 25, 2012, NASA formally announced that Voyager 1 had crossed the heliopause and entered interstellar space. The announcement was carefully worded, but the headline version was simple. Humanity's spacecraft had left the solar system. 45 years after launch, 32 years beyond its 5-year design life, a machine running on the computing equivalent of a pocket calculator had crossed into the space between stars. It was an extraordinary moment in the history of exploration. The data that supported the announcement was real and measurable. Galactic cosmic rays, the high-energy particles that fill the interstellar medium and are partially blocked by the heliosphere, rose sharply. Solar energetic particles, produced by activity on the star at the solar system's center, dropped significantly. The plasma density, estimated through the plasma wave subsystem after the primary plasma instrument had failed years earlier, showed a jump of roughly 80 times compared to heliosheath values. These were consistent with a transition into interstellar space. The announcement was justified by the evidence, but the magnetic field did not cooperate. The interstellar magnetic field had been predicted to lie in a specific direction, estimated from decades of observations made from within the solar system and from data gathered by other instruments. When Voyager 1 crossed the heliopause, the magnetic field it measured was approximately 40 degrees off from the expected interstellar direction. Not slightly off. 40 degrees is a large angular discrepancy. The field had shifted from its heliospheric orientation, which the models had predicted it would do at the crossing, but it had not arrived at the expected interstellar orientation. It sat somewhere in between. It pointed in a direction that nobody had predicted. NASA made the announcement anyway, because the weight of evidence supported the crossing. The magnetic field anomaly was real, but the other indicators were clear. The official position was that Voyager 1 had entered interstellar space. Individual scientists, including some on the Voyager team itself, continued to debate what the magnetic field was doing. Some argued that the anomaly was evidence the crossing was not complete, that the spacecraft remained in some transitional region. Others argued that the interstellar magnetic field near the heliopause simply did not have the orientation the models had predicted, and that the models needed revision. The debate did not end with the announcement. It continued for years. The magnetic field anomaly persisted. As of the years following the 2012 crossing, the field was still roughly 40 degrees from the expected interstellar direction, still slowly evolving, still not matching what the models said interstellar space should look like magnetically. The timeline for how long this discrepancy would persist would eventually extend to 14 or more years post-crossing, with no clear convergence in sight. The crossing of the heliopause by Voyager 1 is confirmed. That much is not in dispute. But what the crossing looked like physically, what the magnetic field at the boundary was actually doing, and whether the spacecraft was in a cleanly defined interstellar environment or in some magnetically complex transition region, remained open questions. The universe at the edge of the solar system was not the well-defined, sharply bounded place that the textbooks had described. It was messier, more layered, and more uncertain than any model had successfully captured, and Voyager 1 kept moving, deeper into whatever that space actually was. Before Voyager 1 crossed into interstellar space, the scientific community had developed a set of expectations about what lay beyond the heliopause. These expectations were based on decades of theory, on measurements made from within the solar system, and on models built from astronomical observations of the interstellar medium as seen from Earth. The general picture was of a relatively calm, uniform environment, not empty, exactly, but quiet. The interstellar medium was known to be a sparse sea of gas and magnetic field, crisscrossed by cosmic rays, with some density variations on large scales. But at the scales Voyager 1 would traverse in a human lifetime, the medium was expected to be essentially stable, smooth, predictable. The data that came back after the crossing said otherwise. The plasma wave subsystem, one of the instruments on Voyager, one that remained operational, is designed to detect oscillations in plasma, the state of matter that makes up most of the interstellar medium. After the heliopause crossing, this instrument began returning data that showed the interstellar medium was significantly more structured than the models had assumed. There were plasma oscillations. There were density variations at scales of multiple astronomical units. There was turbulence. The interstellar medium was not quiet. It had currents, wave modes, and density fluctuations that the pre-crossing models had not incorporated. This finding was not a minor revision at the edges of the expected range. The models had treated the local interstellar medium as relatively uniform at the scales Voyager 1 would sample. The actual data showed variations that required fundamentally more complex descriptions. The interstellar medium has structure at scales that matter for a spacecraft traveling at roughly 38,000 miles per hour. That structure influences how cosmic rays propagate. It influences the shape and behavior of the heliosphere from the outside. It influences how the solar system interacts with the galaxy around it. Getting that structure wrong meant that a significant portion of heliospheric physics, built on assumptions about what the medium outside the heliosphere looks like, needed reconsideration. The findings aligned with and reinforced what was already becoming a recurring theme in Voyager 1 science. Every time the spacecraft reached a new region, the data challenged the assumptions that had been used to model that region. The termination shock had been in the wrong location, and the cosmic ray acceleration happened differently than predicted. The heliosheath had been thinner than expected. The heliopause magnetic field was oriented differently than expected, and now the interstellar medium itself was structured in ways the models had not captured. Each boundary, each new regime, turned out to be more complex than the prior framework described. What this suggested to researchers was not that the models were badly constructed, they were built from the best available data at the time. The problem was that the best available data, gathered from inside the solar system looking outward, was insufficient to capture the actual character of the region beyond. Voyager 1 was doing something that could not have been done any other way. It was providing in situ measurements, direct contact with interstellar plasma, at a distance no other instrument had reached. Each measurement was a correction to an assumption that had previously gone uncontested, because there had been no way to test it. More corrections were coming. The spacecraft was already detecting something that would take years to fully characterize and that had never been heard before by any instrument in history. In 2021, a paper published in the journal Nature Astronomy described something Voyager 1 had been detecting since at least 2017 and possibly earlier. The plasma wave subsystem, one of the few science instruments still operational on the spacecraft, had been registering a faint, persistent signal at a frequency of approximately 2.6 kHz. This signal was not associated with solar storm events. It was not a burst phenomenon that appeared during periods of heightened solar activity and faded afterward. It was continuous, a narrowband hum, constant in character, present in the data day after day, year after year. It arose from the interstellar plasma through which Voyager 1 was moving. This was the first detection of the ambient plasma sound of interstellar space. Previous detections of plasma waves in the interstellar medium had all been connected to solar eruptions, events powerful enough to drive disturbances outward through the heliosheath and into the interstellar medium. These events produced measurable plasma oscillations at Voyager 1's location. Those were event-driven signals. What the 2021 paper described was different. A background signal, present in the absence of any triggering event. It arose from the properties of the interstellar medium itself. The physics underlying the detection is specific. Plasma has a characteristic oscillation frequency called the plasma frequency, which depends on the density of free electrons in the medium. By measuring the frequency at which Voyager 1's plasma wave subsystem detected the hum, researchers could calculate the electron density of the surrounding interstellar plasma. The measured frequency of approximately 2.6 kHz corresponded to an electron density of roughly 0.11 electrons per cubic centimeter. This was not a new kind of measurement for the instrument, but it was the first time it had been applied to a continuous background signal in the interstellar medium rather than an event-driven one. What the measurement provided was a direct characterization of the local interstellar cloud, the particular region of the interstellar medium through which the solar system is currently traveling. By comparing the density readings at different points along Voyager 1's trajectory, researchers found that the local interstellar cloud was not uniform. The electron density varied from point to point. This indicated internal structure. The interstellar cloud had regions of higher and lower density, texture at scales that could be sampled by a spacecraft moving at 38,000 miles per hour over years. This opened the possibility of using Voyager 1 not just as a boundary detector, but as a probe capable of mapping the structure of the interstellar medium as it moved through it, a new kind of cartography, conducted by an instrument nobody had designed for this particular measurement. The discovery raised more questions than it answered. If the local interstellar cloud has internal density structure, what drives that structure? How does it interact with the heliosphere? How representative is the small region Voyager 1 can sample of the broader interstellar environment? These questions cannot be answered by Voyager 1 alone. The spacecraft's trajectory is fixed, its remaining operational lifetime is finite, and its position represents a single line through a three-dimensional medium. But the hum it detected confirmed something that was not in the pre-crossing models. The interstellar medium is not silence. It has its own voice, and Voyager 1 was running on aging hardware 15 billion miles from Earth. It had been the only instrument close enough to hear it. More than 14 years after Voyager 1's heliopause crossing in August 2012, the magnetic field measured by the spacecraft remained approximately 40 degrees off from the expected direction of the interstellar magnetic field. This was not an instrument failure. The magnetic field sensor was functioning. The readings were consistent and reproducible. The field was simply not where the models said it should be. To understand why this mattered, it helps to understand what the interstellar magnetic field direction represents. The interstellar medium is permeated by a magnetic field that threads through the galaxy on vast scales. This field has a measurable direction that can be estimated from astronomical observations and from data gathered by missions designed to detect the energetic neutral atoms flowing into the solar system from outside. The Interstellar Boundary Explorer satellite, launched in 2008, gathered data that allowed researchers to estimate the direction of the interstellar field with reasonable confidence. That direction served as the target prediction for what Voyager 1 should measure once it crossed the heliopause. 14 years after the crossing, the spacecraft's measured field was still 40 degrees away from that target. A 2015 paper proposed a specific explanation: the region immediately outside the heliopause, rather than being a clean transition from heliospheric to interstellar conditions, might instead be a thick magnetic boundary layer that extended 18 or more astronomical units outward from the heliopause, composed of magnetic field lines from both the heliosphere and the interstellar medium that had reconnected and mixed. In this model, Voyager 1 would still be passing through this mixed boundary layer years after the official heliopause crossing, slowly working its way through a magnetically complex transition zone before eventually reaching field conditions that genuinely matched the undisturbed interstellar medium. The field direction would rotate slowly as the spacecraft moved through this layer, eventually converging on the expected interstellar direction. The problem was that the convergence was not obviously happening at the pace the model predicted. The field was rotating slowly, but the rate and trajectory of that rotation did not clearly confirm the boundary layer hypothesis. An alternative explanation held that the models of the interstellar field direction were simply wrong, that the true, undisturbed interstellar field in the local region surrounding the solar system was oriented differently than the interstellar boundary explorer data suggested. In this case, Voyager 1 might already be sampling the genuine interstellar field, and it was the prediction, not the measurement, that needed revision. Both hypotheses remained live as of the years following the crossing. No resolution had been achieved by the available evidence. The spacecraft's limited instrument suite was operating on dwindling power reserves. It could not provide the additional measurements that would cleanly distinguish between the two explanations. Other data sources helped constrain the models, but did not eliminate either possibility. This was science in a state of genuine uncertainty, not the performed uncertainty of a field that already knows the answer, but real, unresolved disagreement about what a specific piece of hardware was actually measuring in a specific location in space. The magnetic field anomaly at the heliopause was one of the most persistent, unexplained features of the entire Voyager 1 dataset. And it existed alongside another anomaly, one concerning the shape of the very structure Voyager 1 had spent decades crossing, because a sphere, it turned out, was probably the wrong shape entirely. One of the fundamental images in space science textbooks is the diagram of the heliosphere, the bubble of magnetic field and solar wind pressure that surrounds the solar system, roughly spherical, centered on the star at its middle, with the termination shock, heliosheath, and heliopause arranged in concentric shells. That image reflected the simplest possible model of a bubble sitting in a relatively uniform external medium. It was a useful starting point. It was also almost certainly wrong. Voyager 1 crossed the heliopause at 122 astronomical units in August 2012. It was heading northward and outward from the ecliptic plane. Voyager 2 followed its own trajectory at a different angle. It crossed the heliopause at 119 astronomical units in November 2018. The crossing distances differed by 3 astronomical units, which might seem small, but represents a measurable asymmetry in a structure that, if it were truly spherical, should show the same boundary at the same distance regardless of direction. The boundary layer thickness at each crossing also differed. This added further evidence that the heliosphere's outer edge was not uniform around its full extent. The numbers from the two spacecraft, combined with data from the Interstellar Boundary Explorer mission, painted a picture of a heliosphere that was not a sphere at all. The data suggested something more like a comet shape, with a rounded nose facing the direction of the solar system's motion through the galaxy, and a long trailing tail extending behind it in the opposite direction. The Interstellar Boundary Explorer, which detects energetic neutral atoms flowing inward from the interstellar boundary, provided the most spatially comprehensive picture of the heliosphere's outer shape, and that picture was decidedly asymmetric. But even with Voyager 1 and Voyager 2 as 2 data points, and the Interstellar Boundary Explorer providing a broader but indirect map, the true shape of the heliosphere remained deeply uncertain. 2 data points on a 3-dimensional surface that spans hundreds of astronomical units in every direction is a very sparse sample. The boundary layer, Voyager 1, found to be thinner than predicted in one direction, might be thicker in another. The heliopause distance might vary by tens of astronomical units around the full sphere of the heliosphere, in ways that no current instrument can resolve. Every textbook diagram of the heliosphere drawn before the late 2010s was not merely imprecise in its proportions, it was wrong in its basic shape. This matters beyond abstract scientific reasons. The heliosphere is, among other things, a radiation shield. It deflects a portion of the galactic cosmic ray flux that would otherwise penetrate more deeply into the inner solar system. The efficiency of that shielding depends on the structure of the heliosphere, its size, its shape, its boundary layer properties, its response to the solar cycle. Getting the shape wrong means getting the shielding calculations wrong. Future crewed missions beyond the inner solar system will need accurate models of that cosmic ray environment. Those models depend on understanding the structure of the shield. That understanding is currently incomplete in ways that matter for human safety planning as much as for pure science. And Voyager 1 gave us 1 data point on the boundary. Voyager 2 gave us a second. There will not be a third for a very long time. The shape of the structure that protects this solar system remains, for now, an educated guess built on 2 trajectories through a surface that spans hundreds of astronomical units in every direction. In 1965, Gary Flandreau calculated that the outer planets would align in a configuration enabling a multi-planet Grand Tour mission only once every 176 years. The window that produced Voyager 1 and Voyager 2 opened in the late 1970s. The next comparable window does not open until approximately the 2150s. That is not a planning horizon. That is a gap spanning several human generations, during which no mission architecturally equivalent to Voyager can be attempted. No replacement mission for Voyager 1 has been funded. Various proposals have been studied. A dedicated interstellar probe mission has been discussed in planning documents for decades, with suggested launch windows in the 2030s and 2040s that would use a close solar flyby for a gravitational slingshot to achieve higher exit velocities than Voyager 1 attained. These proposals have not advanced past the study phase. The funding commitments needed to build and launch such a mission have not materialized. The scientific consensus on the value of such a mission is clear. The political and budgetary support has not matched it. Voyager 1 is currently moving at approximately 38,000 miles per hour. At that speed, it would take the spacecraft roughly 40,000 years to travel to the nearest star system. It will never arrive there. It is not aimed at that destination, and its trajectory will carry it through empty interstellar space for an incomprehensible timescale without encountering any star. The spacecraft will cease being scientifically operational long before it gets close to anything. Current power budget projections suggest that Voyager 1 will be unable to power its remaining science instruments by approximately 2036. After that, it will still be moving, but it will be silent. New Horizons, the spacecraft that flew past Pluto in 2015 and is heading outward in the general direction of the interstellar boundary, is moving more slowly than Voyager 1. It will not reach the termination shock for decades. After that, it would take many additional decades to cross the heliosheath and reach the heliopause. By the time New Horizons could contribute interstellar medium measurements comparable to what Voyager 1 is providing now, Voyager 1 will have been silent for a generation. There is no continuous relay. There is a gap coming in humanity's direct sampling of the interstellar medium, and that gap could last a very long time. After Voyager 1 goes silent around 2036, the open questions from its measurements will remain open. The magnetic field anomaly that persisted for over 14 years, the structure of the interstellar medium, the true shape of the heliosphere, the electron density variations in the local interstellar cloud. These will be studied from Earth-based observatories and from instruments that detect indirect signals. But direct measurement, the kind Voyager 1 has been providing uniquely for over a decade, will stop. This is the context in which the November 2023 crisis must be understood. When Voyager 1's flight data system started producing gibberish, engineers were not just fighting to save an old spacecraft. They were fighting to preserve the only instrument humanity currently has in interstellar space, an instrument that cannot be replaced for generations. It is transmitting data that will not exist again for a timeline that exceeds any reasonable planning horizon. That is why Suzanne Dodd called it one of the most serious crises the mission had ever faced. Because it was. On November 14th, 2023, the team at the Jet Propulsion Laboratory noticed something wrong. The telemetry coming back from Voyager 1 was garbled, not missing, not silent. Garbled. The spacecraft was still transmitting, still using power, still pointing its antenna at Earth. But the data stream coming through was pure gibberish, a repeating binary pattern that made no scientific sense whatsoever. The flight data system, the onboard computer responsible for packaging science and engineering data into a format that Earth could decode, had locked itself into a loop. It was transmitting the same corrupted sequence over and over. Whatever command engineers sent, the response was the same meaningless string of ones and zeros. The first instinct, the very human instinct, was that something extraordinary had happened in interstellar space. Voyager 1 was more than 15 billion miles away. It was drifting through a region of space no human-made object had ever reached. Nobody truly knew what interstellar space contained at that scale. Maybe the spacecraft had passed through something. A dense plasma filament, a region of compressed magnetic field that the models hadn't predicted. Maybe the interstellar medium had done something to the electronics that nobody had anticipated. That instinct felt reasonable. It felt scientifically appropriate. The spacecraft was somewhere genuinely unknown, and when something genuinely unknown happens in a genuinely unknown place, the reasonable assumption is that the unknown place is responsible. It took days to establish that the assumption was wrong. The round-trip signal time in late November 2023 was approximately 45 hours. A command sent from Earth arrived at Voyager 1 roughly 22.5 hours later. The response arrived back on Earth another 22.5 hours after that. Engineers couldn't run experiments quickly. Every test was a 2-day wait. Every hypothesis required patience that most scientific troubleshooting simply doesn't demand. Over the following weeks, the team painstakingly eliminated possibilities. The antenna was working, the transmitter was working, the power systems were nominal. The spacecraft was physically intact by every external indication. The problem was isolated, eventually, to the flight data system itself, specifically to a section of its memory. Somewhere inside the flight data system, a chip had failed. Not catastrophically, not in a way that shut the system down. It had failed in a narrow, localized way. About 3% of the flight data system's total memory had become corrupted. The chip, responsible for storing part of the software that packaged telemetry data, was no longer reading or writing correctly. The spacecraft was running its code, hitting that corrupted section, and spitting out garbage instead of science. It wasn't interstellar space. It wasn't a magnetic anomaly or a plasma event or a collision with some exotic particle. It was a chip. A half-century-old chip, running code written before the personal computer existed, that had finally degraded beyond function. The cause was mundane. The fix was not. The corrupted chip could not be replaced. It could not be rebooted into good health. The physical damage was permanent. To restore function, engineers would need to rewrite the software itself, restructure how the flight data system used its own memory, and do all of it from 15 billion miles away, across a 45-hour round-trip delay. Using documentation written in the 1970s, Nobody had ever attempted anything like it. The question was whether it was even possible. The team at JPL knew what the problem was: a corrupted chip, a damaged section of memory, software that could no longer function as designed. They knew the location of the problem. What they didn't know was how to fix it, and before they could fix it, they had to understand it in a way that nobody alive had understood it in decades. The flight data system aboard Voyager 1 was designed and built in the 1970s. The engineers who assembled it, who wrote its software, who mapped every memory address and every subroutine, had long since left JPL. Some had retired, many had died. The documentation they left behind was incomplete, inconsistent, and written for a world in which the hardware itself still existed somewhere on Earth that people could examine directly. No such hardware exists anymore. The flight data system is a one-of-a-kind machine, and the only copy of it is 15 billion miles away. Suzanne Dodd, the project manager for the Voyager missions, led the team through what amounted to an archaeological excavation. They pulled archival documents from storage, printed manuals, handwritten notes, internal memos from engineers who had been working on microcomputers before microcomputers were a common concept. They digitized what could be digitized. They cross-referenced. They looked for contradictions between documents and tried to determine which version of the record was accurate. The challenge wasn't just reading old documents. The challenge was understanding a system whose logic had been built for constraints that no longer applied, written in an assembly language that modern engineers rarely use, describing hardware whose behavior under 5 decades of radiation exposure was not something any manual had anticipated. Every memory address mattered. The flight data system has 69 kilobytes of total memory. 69 kilobytes. A single low-resolution photograph from a modern smartphone contains more data than the entire working memory of the most distant spacecraft humanity has ever built. Within those 69 kilobytes, the team needed to identify not just where the corruption was, but what the uncorrupted code was supposed to do, what it called, what called it, and what would break if any single reference was changed. This is the kind of software archaeology that almost never happens, because almost no system survives long enough to require it. Software gets replaced, hardware gets upgraded, the whole stack turns over. But Voyager 1 has been running the same code on the same hardware for nearly 5 decades. There was no upgrade path, there was no rollback option, there was only the documentation, the current state of the machine, and the gap between them. Engineers worked in rotating shifts. They modeled the memory layout as best they could reconstruct it. They traced execution paths through the code based on archival descriptions of what the system was supposed to do. They built a picture of the flight data system from the outside in, from documentation backward toward reality, across a 22.5-hour signal delay that made every verification test an almost day-long commitment. The work took months, not because the engineers were slow, because the system was genuinely complex. The records were genuinely incomplete, and every test required waiting half a day just to find out whether the question had been answered correctly. By early 2024, they believed they understood the system well enough to attempt something. The question was whether their understanding was correct. In March 2024, after months of archival research and memory reconstruction, the team was ready to try something that had never been attempted in the mission's history. They would send a command to Voyager 1 asking it to dump the entire raw contents of the flight data system's memory, not packaged, not formatted, not filtered through the corrupted software routines that had been garbling the data since November. Raw. Whatever was in memory, bit by bit, transmitted directly back to Earth. The command was sent on a Thursday morning. Then the team waited. 22.5 hours for the signal to reach Voyager 1, 22.5 hours for the response to travel back. The engineers who sent the command would not know whether it had worked until the following Friday. There was nothing to do during that window except keep the Deep Space Network's antennas pointed at the right part of the sky and wait. When the data arrived, it was 70 kilobytes of raw memory, 70 kilobytes that contained the entirety of what the flight data system knew about itself and its current state. The team had never seen the machine's memory laid bare like this before. It was, in a sense, the most complete picture anyone had ever had of what was happening inside Voyager 1's brain. The analysis took days. The process was painstaking, cross-referencing half-century-old documentation against raw binary data, section by section. Researchers went through the memory map they had reconstructed from archival documents and compared it against what the dump revealed. Most of the memory matched what the documentation predicted. Most of it was intact. The code was where it was supposed to be. The data tables were where they were supposed to be. And then there was the section that wasn't. A single contiguous block, representing approximately 3% of the flight data system's total memory, was corrupted. The bit patterns inside that block were inconsistent with any valid instruction or data state the system should have been able to reach through normal operation. The corruption was localized. It wasn't scattered. It occupied one specific region, a block that sat in a single physical chip inside the hardware. The pattern of the corruption was consistent with physical damage, not a software error, not a logic fault. Physical degradation. The chip itself had been changed by something. Most likely, either the cumulative effect of nearly 5 decades of operation or a single high-energy particle, a cosmic ray that had passed through the chip and flipped bits that could not be unflipped. This mattered enormously. If the corruption were distributed randomly across memory, the problem would be nearly impossible to address. Random corruption means nothing is reliable. But corruption confined to a single physical block meant the rest of the system was intact. The software could be rebuilt. The code could be moved. The functions that had been stored in the damaged region could, in theory, be relocated to somewhere else. The dump had given the team what they needed, a precise map of the damage. They knew exactly what was broken, exactly where it was, and exactly what space remained in the rest of memory. Now they had to figure out what to do with that knowledge, and how to do it from 15 billion miles away. The problem was clear. The solution was not obvious, but it existed. The corrupted chip inside Voyager 1's flight data system was physically destroyed. No signal from Earth could repair damaged silicon. The bits that had been flipped by radiation or age would not unflip. That section of memory was gone, and whatever code had been stored there could no longer run from that location. But the rest of the flight data system's memory was intact. 69 kilobytes total, roughly 3% destroyed. That meant roughly 67 kilobytes still available, scattered across the remaining chips in non-contiguous blocks. The question was whether the code that had been lost in the damaged section could be broken apart, redistributed across those scattered fragments of available memory, and rewoven together in a way that still functioned. The engineers decided it could be done. The work was unlike any software repair in history. Normally, when software is fixed, you can test it locally. You compile, you run, you observe the result in seconds or minutes. If it breaks, you look at what broke and try again. The feedback loop is tight, the iteration is fast. For Voyager 1, the feedback loop was 45 hours. Every modification to the flight data system's code had to be transmitted, had to travel 22.5 hours through space, had to be accepted and executed by the spacecraft, and the result had to travel 22.5 hours back. Each test cycle was nearly 2 full days. A mistake wasn't a quick debug session. A mistake was a 2-day setback at minimum, and in the worst case, a mistake could permanently damage a system that could not be reset to a known good state. The team worked methodically. They relocated sections of code, one piece at a time. When a section moved, every pointer referencing it had to be updated. Every subroutine that called into the relocated code had to be told where the code had moved. The entire data packaging system, the routines responsible for collecting science and engineering measurements and assembling them into a transmissible format, had to be rebuilt, distributed across non-contiguous memory islands. On April 20th, 2024, the engineering data stream came back, not garbled, not corrupted, clean. The flight data system was packaging and transmitting its internal housekeeping data correctly for the first time since November. The team had been working on this for 5 months. The moment the clean data arrived, engineers who had been rotating through 12-hour shifts at JPL knew that the surgery had worked. But 4 science instruments were still offline. Each one required its own software restoration, its own careful relocation, its own 45-hour verification cycle. Through May and into June, the team brought the instruments back one by one. In June 2024, all 4 instruments came back online: the magnetometer, the plasma wave system, and the 2 remaining particle detectors were running again. Voyager 1 was doing science again, from 15 billion miles away, after 5 months of silence, after the most remote software repair operation in the history of space exploration. The mission had been saved, but saved for how long? The power systems were aging faster than any code could fix, and the numbers had been running in one direction for a long time. When Voyager 1 launched in 1977, its 3 radioisotope thermoelectric generators produced approximately 470 watts of electrical power. The generators worked by converting heat from the radioactive decay of plutonium-238 into electricity. Plutonium-238 has a half-life of about 88 years. This meant the decay rate, and therefore the heat output, and therefore the electricity, was always going to decrease, slowly at first, then more noticeably, then inexorably. By the mid-2000s, the generators were producing significantly less power than at launch. The team had been managing the decline for decades, carefully prioritizing which systems got power and which were shut down. Heaters that kept instruments from freezing in deep space were turned off one by one, accepting that some hardware would reach temperatures it was never designed to survive, because the alternative was shutting down something that was still returning data. The rate of power loss is roughly 4 watts per year. 4 watts sounds small, but when the total available power is already a fraction of what it was at launch, 4 watts per year is a steady erosion of options. Every watt saved by shutting one instrument down buys a little more time for the ones still running. On February 25th, 2025, mission controllers shut down the cosmic ray subsystem. This instrument had been measuring the flux of cosmic ray particles entering the heliosphere and crossing into interstellar space. It had data going back 47 years. It was shut down not because it had failed, but because the spacecraft no longer had enough power to run it alongside everything else. The choice was made deliberately, and it was not reversible. The low-energy charged particle instrument is scheduled to be shut down in 2026. After that, only 2 instruments will remain active: the magnetometer, which measures the direction and strength of the local magnetic field, and the plasma wave system, which measures plasma density through the electromagnetic hum the environment produces. The mission end date, based on current power projections, is approximately 2036. That is the year when the remaining power will no longer be sufficient to operate the transmitter and the science instruments simultaneously. After that, Voyager 1 will still be out there. It will still be drifting through interstellar space at roughly 38,000 miles per hour, but it will no longer be talking. Every instrument shutdown is a permanent narrowing of what can be known. The cosmic ray data that the cosmic ray subsystem would have collected between now and 2036 will never exist. Nobody will know what that instrument would have observed. Its unique vantage point, more than 15 billion miles from the star, measuring particles that travel across the galaxy, is gone forever from the record. The magnetometer and the plasma wave system will continue until the power runs out. 2 instruments, from a position no other spacecraft will occupy for at least decades, possibly a generation. The data they return is not redundant. There is no backup. No satellite in orbit around Earth is measuring what these 2 instruments measure from this location, in this direction. The clock is running. It has always been running. But the window between what Voyager 1 could still discover and the moment the transmitter goes quiet is now visible, and it is not as wide as the scientists watching that window would like. When the Voyager missions were conceived, the assumption was that they would pioneer a path that others would follow. That is how exploration has historically worked. Someone goes first and establishes what is there, and then the next generation builds on what the pioneers found. The first probes to Mars were followed by landers and rovers. The first spacecraft to reach the outer planets opened the door for orbiters and atmospheric probes. The expectation was that deep space, interstellar space, would follow the same pattern. It hasn't. Voyager 2 is currently at approximately 157 astronomical units from the star. 1 astronomical unit is the average distance from Earth to the star, roughly 93 million miles. Voyager 2 is in interstellar space, but it crossed the heliopause in a different location and a different direction than Voyager 1. The two spacecraft are not duplicates of each other's data. They are sampling two different points in the heliosphere's boundary, and both are irreplaceable. New Horizons, the spacecraft that flew past Pluto in 2015, is heading outward, but it is moving more slowly than the Voyager spacecraft, and it lacks the instruments to do magnetospheric and plasma science at the level the Voyager probes can. It will not reach the termination shock for decades. It will not reach the heliopause within any time frame that helps with the questions Voyager 1 is currently generating. No replacement mission is funded. The interstellar probe concept has been studied by NASA and by the scientific community for years. It exists as a proposal. It describes a spacecraft that could travel faster than the Voyagers and carry more capable instruments. It identifies what science could be done and what questions could be answered. It sits, unfunded, in a queue of proposals that will require political decisions that have not been made. The funding cycle for deep space missions is long. A mission approved today would take years to design, build, test, and launch. A mission designed to reach interstellar space would take decades more to get there. Even an optimistic scenario, a mission funded within the next few years and built faster than the Voyager missions were built, would not return interstellar data until sometime in the second half of this century. When Voyager 1 goes silent around 2036, humanity will have 0 operating spacecraft in interstellar space. Voyager 2 may remain operational slightly longer or slightly shorter, depending on how its power systems hold out. At some point in the late 2030s or early 2040s, both spacecraft will fall silent. After that, there is nothing. Scientists who were children when Voyager 1 crossed the heliopause may be retired before any follow-on mission returns interstellar data. An entire generation of space scientists may do their entire careers without access to in-situ measurements of interstellar space. The people who designed the Voyager missions assumed this problem would have been solved by now. They assumed the scientific value of interstellar data was self-evident enough that funding would follow. They were wrong about that. What Voyager 1 found when it got here was strange enough that not having a follow-up instrument is not just a gap in the record. It is a gap in what science can say with any confidence. And right now, there is no plan to fill it. One of the strangest instruments Voyager 1 carries is the plasma wave system. Its job is to detect electric and magnetic field oscillations in the plasma surrounding the spacecraft. In the region of interstellar space, where Voyager 1 now travels, the plasma is extraordinarily thin. There are perhaps a few electrons per cubic inch, but even that sparse population of charged particles has structure. It oscillates, it hums, and the frequency of that hum tells scientists something they can measure nowhere else. The hum is not a recording of sound. Space is not a medium that carries sound in the ordinary sense. What the plasma wave system detects are electron plasma oscillations, waves in the density of free electrons that propagate through the medium. The frequency of those oscillations is directly tied to the density of the plasma. A higher frequency means denser plasma. A lower frequency means less dense plasma. Every measurement the instrument takes is, in effect, a density reading of the local interstellar medium. Since Voyager 1 crossed the heliopause in August 2012, the plasma density it has measured has been rising, slowly but consistently. The frequency of the hum has been climbing in a way that was not predicted by models of the local interstellar medium. The region outside our heliosphere was supposed to be relatively uniform at the scale Voyager 1 is traversing. It is not. It is getting denser. There are two serious interpretations of this trend, and scientists have not yet been able to choose definitively between them. The first interpretation is structural. The local interstellar cloud, the region of interstellar gas through which our entire stellar system has been traveling for the past 100,000 years or so, may not be uniform. The heliosphere may be moving through it, and Voyager 1 may now be in a part of the cloud that is intrinsically denser than the part it was in when it first crossed the heliopause. On this interpretation, the rising density reflects the actual geography of the local interstellar medium. The second interpretation is positional. The heliopause is not a clean boundary. It is a thick, turbulent transition zone. Voyager 1 may still be embedded in the outer edges of this transition zone, sampling plasma that is influenced by both the heliosphere and the broader interstellar medium. On this interpretation, the rising density is a boundary effect, and the true density of deep interstellar space has not yet been sampled. The distinction matters enormously. If the first interpretation is correct, the density profile Voyager 1 is building is a map of the interior of the local interstellar cloud, a first ever measurement of a structure that has never been directly sampled. If the second interpretation is correct, the transition zone is far thicker than models predicted, which means everything scientists thought they knew about the heliopause boundary is wrong. Both interpretations are scientifically explosive, but they are different explosions, and right now, both remain possible. The plasma wave system is watching for a density plateau or a sharp change that might settle the question. A plateau would suggest the spacecraft has reached a stable region of interstellar space. A sharp change might mark a boundary inside the cloud itself. Neither has happened yet. The hum keeps climbing, and the question it is asking keeps getting louder. The November 2023 crisis had barely been resolved when Voyager 1 did something unexpected again. In October 2024, a power fault aboard the spacecraft triggered an automatic protection response, a protection routine built into the hardware. One of those safeguards written into the system in the 1970s activated and switched the main transmitter off its primary frequency. The spacecraft began broadcasting on a backup frequency that had not been used in years. Nobody at JPL was listening on that frequency. The Deep Space Network, the global array of giant dish antennas that maintains contact with all of NASA's deep space missions, was pointed at the right part of the sky. The antennas were functioning. The receivers were active, but they were tuned to the frequency Voyager 1 was supposed to be using, the frequency it had been using for years. The backup frequency wasn't being monitored. From the perspective of everyone on Earth, Voyager 1 had gone silent. It hadn't gone silent. It was transmitting continuously, as it has done for 47 years. The signal was there, crossing 15 billion miles of space at the speed of light, arriving at Earth on schedule, and landing in a part of the radio spectrum where nobody was looking for it. The team at JPL recognized what had happened by working backward through the engineering data that had been received before the switch. The power fault was identifiable in the record. The protection routine that responds to power faults was known. The backup frequency that routine would switch to was documented. Engineers retuned the Deep Space Network receivers to the backup frequency and waited. On November 18, 2024, communications were restored. The spacecraft was healthy. The science instruments were running. The data gap in the record was a little over a month, but the mission itself was intact. What the October 2024 event illustrated was something more disturbing than a simple technical fault. It illustrated how fragile the communication link actually is. Voyager 1 is, in some sense, running on autopilot. The spacecraft's onboard systems make decisions autonomously. Protection routines activate when conditions cross certain thresholds. Mode switches happen automatically. And the 45-hour round-trip delay means that when the spacecraft does something unexpected, it will have been doing it for nearly 2 days before Earth even knows. Any mode change that is not correctly anticipated, any automatic response that engineers don't immediately recognize from the downstream data, is a potential mission-ending event. Not because the spacecraft breaks, but because the communication link could be lost before the problem is identified. And restoring a lost communication link requires knowing what the spacecraft did and knowing what command to send across a 45-hour feedback window. The older the spacecraft gets, the more likely these unexpected automatic responses become. Systems that have been running for nearly 50 years degrade, thresholds shift, behaviors drift. A protection routine designed for a certain power state may activate at a different power state than intended, because the hardware that reports power levels is not reading the same way it read in 1977. Each unexpected event is survivable until one isn't. The mission has now had 2 major crises in 13 months. The question of whether a third one can be managed successfully across an ever-growing signal delay is one that nobody at JPL can answer with certainty. Attached to the outside of Voyager 1's body is a 12-inch disc made of copper plated with gold. It is sealed in an aluminum cover inscribed with instructions for how to play it. It carries 115 images encoded in analog form. It carries greetings in 55 human languages. It carries natural sounds of Earth, music from across human history and across cultures, and mathematical diagrams intended to help whoever finds it understand the basic structure of the civilization that sent it. And it carries something else, something that nobody talks about as often, but that might be the most striking thing on it. Anne Druyan was the creative director of the Golden Record project. She and Carl Sagan, who led the project, fell in love while working on it. A decision was made to record Druyan's brainwaves, the actual electrical activity of her thinking mind, and encode that recording on the disk. The brainwave recording was made while she thought deliberately about specific things, about the history of humanity, about the present moment, about what she hoped. At the moment the recording was made, she had just learned that she and Sagan were going to spend their lives together. That knowledge was in her mind while her brainwaves were being captured. Those brainwaves are now more than 15 billion miles from Earth. They are moving away at roughly 38,000 miles per hour and have been doing so since September 1st, 1977. The Golden Record was designed to last 1 billion years. The copper underneath the gold plating will not significantly corrode in the vacuum of interstellar space. The information encoded in its grooves will remain readable by whatever instrument could read it for a time that makes all of human history look like an afternoon. The record will outlast every building on Earth. It will outlast the planet's oceans. It will outlast Earth itself, which will be consumed when the star enters its red giant phase in approximately 5 billion years. It will outlast the star. The record is the farthest traveled artifact of human consciousness that has ever existed. It is not a machine. It does not measure anything. It does not transmit. It simply is, out there, moving through interstellar space with everything it contains, waiting. Sagan said many times that the Golden Record was as much a message to ourselves as to any hypothetical recipient. The act of choosing what to put on it, of deciding what represented humanity and what music was worth hearing and what images captured something essential, forced the people who made it to answer questions about what humanity actually is and what it values. The record is a mirror as much as a message. Whether it will ever be found by anyone is genuinely unknowable. The star system Voyager 1 will pass closest to is about 17 light-years away, and Voyager 1 will make its closest approach in approximately 40,000 years. The probability that any intelligence will intercept it is By any realistic estimate, extraordinarily small. But the disk is there, traveling, carrying the brainwaves of a woman who fell in love, the music of people who never imagined anything would carry their songs to the stars, and the image of a pale blue dot that is already shrinking in the very direction the spacecraft has left behind. In 2026, 49 years after launch, Voyager 1 still has 4 measurements that its data generates, and that no existing model of the interstellar medium fully explains. These are not minor discrepancies. They are not rounding errors. They are fundamental gaps between what physics predicted would be true and what the spacecraft is actually observing. The first is the magnetic field direction. When Voyager 1 crossed the heliopause in 2012, scientists expected the interstellar magnetic field to be aligned at a specific angle relative to the direction of the heliosphere's motion through space. The alignment predicted by models was based on decades of remote observations of polarized starlight, which carries information about the magnetic fields it travels through. The models predicted an angle. Voyager 1 measured an angle. The two differed by more than 40 degrees. 14 years later, with continuous measurements from the magnetometer, the discrepancy has not resolved. The magnetic field outside the heliosphere points in a direction that models of our galactic neighborhood did not predict. The second is the thickness of the heliosheath, the region between the termination shock and the heliopause. Models predicted a thickness of somewhere between 100 and 150 astronomical units. The actual measured thickness was between 25 and 30 astronomical units. The models were off by a factor of 3 to 4. The heliosheath is dramatically thinner than anyone expected, which means the compression of solar wind at the boundary is dramatically more efficient than models accounted for. No fully accepted explanation exists for why. The third is the plasma hum. As discussed previously, the density of plasma in the interstellar medium is rising steadily, but the character of the hum itself is disputed. Some researchers interpret it as thermal noise, the random electromagnetic emission of a warm plasma. Others interpret it as organized wave propagation, which would imply structure and dynamics in the interstellar plasma that models did not include. The distinction matters for understanding the physical processes at work, and the data does not yet cleanly distinguish between the two interpretations. The fourth is the rising density trend itself. Even setting aside what the hum means physically, the continuous increase in measured plasma density since 2012 is something no model predicted. Whether it reflects the spacecraft's position in a boundary layer, or the actual large-scale structure of the local interstellar cloud, or something else entirely, remains unresolved. 4 anomalies, 4 significant departures from prediction. And the instrument that could resolve them, the instrument that is producing this data, is running on a power budget that shrinks by approximately 4 watts every year. The magnetometer and the plasma wave system will continue until the power runs out. Every other instrument that might help distinguish between competing explanations is already shut down or scheduled to be shut down. The particle detectors that could help separate boundary layer effects from deep interstellar effects are gone or going. What remains is 2 instruments in one location measuring 2 things. That has to be enough, because nothing else is out there. The 4 anomalies might be resolved before the mission ends. They might not. If they are not, they will sit in the scientific record as questions that the only machine that could answer them ran out of power before it could. The story of every major Voyager 1 boundary crossing has the same structure. Scientists build the best model they can from observations available at the time. The model makes predictions. Voyager 1 arrives at the boundary. The predictions turn out to be wrong, not slightly wrong. Wrong in ways that require fundamental revision. This has happened at every major boundary the spacecraft has crossed. At the termination shock, where solar wind particles slow from supersonic to subsonic speeds, the predicted geometry was wrong. Models said the heliosphere should be roughly symmetric, shaped more or less like a sphere, slightly compressed in the direction of motion. The data from both Voyager spacecraft suggested the shape was far more asymmetric. The termination shock on the side facing the direction of the heliosphere's motion through interstellar space was closer to the star than predicted. The boundaries were not where they were supposed to be. In the heliosheath, the region of decelerated solar wind between the termination shock and the heliopause, models failed to account for the compression mechanisms that would produce the thin heliosheath the spacecraft actually measured. Solar wind particles in the heliosheath were interacting with each other and with interstellar neutrals in ways that models had not fully included. The result was a boundary region 3 to 4 times thinner than predicted. At the heliopause itself, models assumed a relatively clean and sharp transition between solar and interstellar plasma. The spacecraft encountered a thick, turbulent transition zone, tens of astronomical units wide. It was not a boundary in the sense physicists typically use the word. It was a mixing region, a zone of competition and interaction that took the spacecraft years to traverse. In the interstellar medium beyond the heliopause, the expectation was relative quiet, a steady, slowly varying plasma with predictable properties. Instead, Voyager 1 has been recording increasing density, direction anomalies in the magnetic field, and a plasma hum that doesn't match the simplest thermal noise models. The pattern is consistent. At every boundary, complexity was underestimated. At every transition, the real physics was richer and less tractable than the models had assumed. This is not an indictment of the scientists who built those models. They built the best models they could from the data available to them. Remote observations of the heliosphere from within it simply cannot capture everything that happens at its edges. The error was not incompetence. The error was the only error that is possible when exploring genuinely unknown territory: extrapolation. Every model was an extrapolation from known physics into unmeasured space, and every extrapolation turned out to underestimate what was actually there. The significance of this extends beyond the heliosphere. Models of how other stars shape their local environments have been built using the heliosphere as the baseline case. The heliosphere was supposed to be the thing scientists understood well. It was the nearest, most studied example. All those other star models were calibrated against the heliospheric picture that turned out to be wrong at every layer. Voyager 1 did not just change what scientists know about our own heliosphere. It changed the reliability of models for every stellar environment ever studied. The error was built into the foundation. Recalibrating every model that relied on the old picture is work that will take years. And the question is how deep that goes. Every star that burns in the sky has, around it, a region shaped by its own stellar wind. The star pours out a continuous stream of charged particles, and those particles push against the interstellar medium and carve out a bubble, a protected zone within which the magnetic field of the star holds sway. For our own stellar system, this bubble is called the heliosphere. For other stars, the equivalent structures are called astrospheres. Astrospheres are too small and too far away to visit. The nearest star to our own is more than 4 light-years distant. Even at Voyager 1's speed, which is faster than any other human-made object has ever moved, it would take approximately 70,000 years to reach that star. Sending a probe to directly sample another star's astrosphere is not something any mission planner is currently contemplating in a practical sense. So scientists study astrospheres the way they study everything that is too far to touch. They observe them with telescopes. Ultraviolet observations from space-based observatories can detect the bow shocks and boundary regions around nearby stars. X-ray observations reveal the thermal structure of stellar winds. Spectroscopic data carries information about the densities and velocities of plasma in stellar environments that can be partly decoded from the patterns in the light. These observations have produced a body of knowledge about astrospheres across a range of stellar types. Scientists have mapped bow shocks, estimated astrosphere sizes, inferred the properties of stellar winds and the local interstellar medium in which different stars are embedded. The field is real and productive and has contributed genuinely to understanding of how stars interact with their galactic neighborhood. All of those models were built on a foundation. They were calibrated using the most detailed and best understood example available, the heliosphere of our own stellar system. The heliosphere was the ground truth. It was where the physics was known, where the numbers could be checked, where the model parameters could be validated before being applied to distant systems. But Voyager 1 has now established that the ground truth was wrong. The shape was wrong. The boundary thickness was wrong. The transition zone structure was wrong. The interstellar plasma properties were wrong. The model of the heliosphere that underpinned every astrospheric model built in the last several decades was a model built without in-situ data from the relevant regions. Now there is in-situ data, 12 years of it, from one location, in one direction. It is imperfect. It is limited. It represents a single narrow sample of an enormously complex system. But it is real data from inside the interstellar medium, and it is already forcing revisions to astrospheric models across the board. In a specific and measurable sense, Voyager 1 has become the calibration instrument for an entire field of astrophysics. The physical processes it measures directly are now used to anchor and correct models of stellar systems that can only be observed remotely. A spacecraft the size of a small car, built in the 1970s, running on 69 kilobytes of memory, is now setting the parameters that modern astrophysicists use when they try to understand how stars shape the space around them. What those corrections reveal about the other stellar systems that have been modeled is still being worked out. How wrong was the old calibration? That question doesn't have a final answer yet. In 2024, with Voyager 1 sitting at approximately 163 astronomical units from Earth, the one-way signal delay was 22.5 hours. A command sent from Earth took that long to arrive. A response took that long to come back. That 45-hour round-trip delay shaped every aspect of the repair work done in 2023 and 2024. It made each diagnostic test a 2-day commitment. It made mistakes expensive. It made patience a technical requirement. By 2036, when the mission is expected to end, the signal delay will be approximately 26 hours each way, 52 hours round-trip. Voyager 1 adds roughly 330 million miles of distance every year because it is moving at approximately 38,000 miles per hour and never stops. Each year, the signal has farther to travel. Each year, the feedback loop grows longer. This is not a problem that engineering can solve. A faster radio transmitter doesn't help because the signal already travels at the speed of light. A more sensitive receiver doesn't help because the limiting factor is not signal strength, it is distance. The physics of electromagnetic communication across interstellar distances is fixed. Light moves at roughly 186,000 miles per second, and that is not negotiable. Any future deep space mission, any probe sent significantly beyond the planetary system, will face the same constraint. A mission designed to reach the termination shock quickly, using a more capable rocket, or a solar sail, or a nuclear propulsion system, might arrive at the heliopause in decades rather than the 35 years it took Voyager 1. But arriving quickly does not make the communication delay shorter. A probe at 100 astronomical units still takes 14 hours to receive a signal from Earth and 14 hours to respond. A probe at 200 astronomical units would face a 28-hour one-way delay. Any deep space mission beyond a certain distance requires the spacecraft to operate autonomously in ways that current spacecraft do not. A spacecraft waiting 45 hours for instructions cannot rely on Earth-based decision-making for anything time-sensitive. If something goes wrong, or if conditions change, or if the spacecraft encounters something unexpected, it must be capable of responding on its own. Humanity has built remarkably capable autonomous spacecraft for planetary science. Mars rovers make decisions about driving and sampling without continuous human input. But the level of autonomy required for a true deep interstellar mission, one that might encounter genuinely novel conditions far outside human experience or modeling, is qualitatively different. It requires the spacecraft to understand its own mission well enough to adapt to situations its designers never anticipated. That kind of autonomy does not yet exist in any spacecraft that has been built or is currently being designed. The gap between the autonomy that current deep space probes have and the autonomy that a mission operating at 50-hour round-trip delays would require is not a gap that will be closed by better software alone. It requires a different philosophy of spacecraft design, and that philosophy takes decades to translate into hardware. The distance from Earth to where Voyager 1 is right now is not just a number, it is a permanent feature of what communication with that spacecraft means. And for any mission that follows, it will be a feature of what operating there means. Two instruments are still running, the magnetometer and the plasma wave system. These are the sensors that will carry the Voyager 1 mission through whatever years remain to it, gathering data from a location no other instrument has ever occupied and no other instrument is scheduled to reach. The magnetometer is watching for a specific thing. The magnetic field of the interstellar medium has been pointing in a direction that disagrees with models by more than 40 degrees, and it has been doing this continuously since 2012. One prediction from the boundary layer interpretation of the heliopause is that this misalignment should rotate. If Voyager 1 is still embedded in the thick, turbulent transition zone that makes up the outer heliopause region, the magnetic field direction should gradually shift as the spacecraft moves deeper into unperturbed interstellar space. The rotation, if it happens, would help confirm that the spacecraft is still transitioning and would let scientists estimate how thick the transition zone actually is. If the field direction stays fixed, that tells a different story. A stable field direction would suggest Voyager 1 has already cleared the transition zone and is sampling the true interstellar magnetic field. A 40-degree disagreement with models would then be a 40-degree disagreement with the entire framework of galactic magnetic field mapping that those models rely on. Both outcomes would be significant. Both would revise something fundamental. The magnetometer is, in effect, running an experiment whose outcome will matter either way. The plasma wave system is watching for a density change. The rising plasma density trend that has continued since 2012 is approaching a point where a decision between the two major interpretations might be possible. If the density reaches a plateau, levels off, and stops rising, that would be consistent with the spacecraft having moved through a boundary layer into a stable region of the local interstellar cloud. If the density continues rising steeply, or if it drops sharply, that would suggest the spacecraft is encountering a structural feature of the cloud itself, possibly its outer edge. The timing is uncertain. The density change that would settle the question might happen next year. It might happen in 2035. It might not happen before the mission ends. Scientists cannot know in advance, because the structure of the local interstellar cloud at this scale has never been directly measured. This is what a scientific frontier looks like from the inside. Two instruments, two questions, a power budget that runs out around 2036. The two measurements might converge into answers, or they might leave the questions half-answered, or they might open entirely new questions that have no instrument to address them. The team at JPL is aware of this. Instrument managers track power consumption week by week. They calculate when each system will need to be shut down to keep the transmitter running. They watch the margin between what the spacecraft needs to function and what the generators can provide. The margin is shrinking. It always shrinks. The question is not whether the power will run out, but whether the data that matters most will arrive before it does. Scientists are racing against a countdown that began the moment the spacecraft was built, in a race that nobody alive will be able to finish for them. There is a machine traveling through interstellar space right now. It is approximately the size of a small car. Its computing power is less than what a modern digital watch contains. It has a memory capacity of 69 kilobytes. It was built using technologies that no longer exist in any factory or laboratory on Earth. The engineers who designed its fundamental architecture are gone. The tools used to program it are obsolete. The computer languages it runs in are taught, if at all, as historical curiosities. It has been operating continuously for more than 47 years. It has crossed the termination shock, crossed the heliosheath, crossed the heliopause, and entered the interstellar medium. At every boundary, the physics it measured was more complex than the models predicted. At every boundary, it returned data that forced revision of something scientists thought they understood. It has never stopped moving. It has never stopped transmitting. It has never done what anyone expected it to do once it got far enough out. In late 2023, a chip inside it failed. A 3% corruption of its memory caused a crisis that took 5 months to resolve. Engineers who had never worked on the original hardware reconstructed the architecture from incomplete records, mapped the damage, redesigned the software to run in the surviving memory, and restored function across a 45-hour round-trip signal delay. The repair worked. The signal from this machine takes more than 23 hours to reach Earth. By the time it arrives, it describes conditions that existed almost a full day ago. Everything scientists know about where Voyager 1 is and what it is measuring is a window into the recent past, and every response they send to it will take more than 23 hours to arrive. 2 instruments are still running. The magnetometer is measuring the direction and strength of the magnetic field. The plasma wave system is listening to the hum of plasma density. Every day, both instruments generate data. Every day, that data makes its 23-hour journey. Every day, it arrives at receiving dishes in California, Spain, and Australia, and is recorded. The spacecraft does not know it is historic. It has no capacity for that. It runs its code. It takes its measurements. It transmits. The transmitter runs because the generators still produce enough power to run it. The generators will keep producing power, declining slowly, until approximately 2036. At some point after that, the transmitter will go quiet. Before that happens, the magnetometer may see the magnetic field rotate. It may not. The plasma wave system may see a density plateau that marks the edge of the local interstellar cloud. It may not. These observations may happen next year. They may happen in the last days of the mission. They may not happen at all. The spacecraft is not hurrying. It moves at 38,000 miles per hour and cannot go faster or slower. It measures what it measures and transmits what it finds. The questions its instruments are asking about the structure of the boundary, about the magnetic field, about what lies farther in the cloud, are not questions it is capable of caring about. Those belong to the people on the other end of the signal. The antenna is still pointed at Earth. The hum is still rising. Something is out there.